Welcome to this new series of videos. Our prep students, like all of you, were forced to stay at home. During this time, we designed an activity called virtual learning and teaching. Basically, our students strengthen the fundamental knowledge of their projects and have prepared some videos that are going to be shared with you. We're going to start with you, Carlos.
Hi, Doctor.
Please tell us a little bit about yourself and what are the potential applications of your research project.
Of course. I am Carlos Mauricio de Leo, and I am majoring in physics and in chemistry at UTRGV. I am also doing a minor in business administration. My goal is to work as a scientist in industry. The focus of this project is to make new magneto-optical materials, which can be used to make dense data storage memory devices, signal processors, antennas, medical imaging, energy technology, and even optical devices like electromagnetic clothes.
Amazing. And you prepare an absolutely amazing and very creative video. I love the way that you explain electron confinement in quite an easy way. And I'm pretty sure all of you are going to enjoy this video. Let's start.
So, what are quantum dots? Quantum dots are small semiconductor crystals. The main property of these crystals is that they are barely a few nanometers in size. That is about 10,000 times smaller than the average hair diameter. This means that quantum mechanics plays a major role in explaining the behavior of these crystals. Making quantum dots in a lab is possible due to the quantum confinement effect. To explain this effect, picture a cubic block of cheese from the supermarket that happens to be as conductive as gold. From an electric cheese atom's perspective, there's a huge amount of cheese making up for the volume of the cheese. The ratio is enormous. There are electrons from the cheese atoms in the surface passing from atom to atom, randomly traveling at different directions. Imagine now that for some reason we are quarantined and it is not possible to go out and get more food. You'd like that block of cheese to be used wisely, so you start cutting slices very thin, to the point that there are more cheese atoms from the slice in the surface than in the volume. This will look like 5 to 10 atoms comprising the surface followed by a few nanometers of volume and again 5 to 10 atoms of surface. Now, the total thickness of our slice is just a few nanometers in size. Since our cheese is electric, electrons are still traveling in random directions, but we observe something new happening. Electrons cannot go up or down because there is nowhere to travel in the third dimension. We have created a two-dimensional thin film structure with the size of a few nanometers. This is called a quantum well. To explain this concept, picture a person at the bottom of a waterless well. The subject can take a few steps around inside the well, but it is unable to travel up or down. It is trapped in a well, and this also happens to electrons. Back to our electric cheese story. We are about to make some sandwiches when someone suggests that cheese strings sound more appealing and that cheese will last more this way. And you get your fresh, ultra-thin quantum well slices and make cuts of the same size perpendicular to the prior cuts. Now you have ultra-thin electric cheese strings that look like miniature cheese wires. The electrons are restricted once more in another direction and can only go forward or backward, like a guy in a tightrope. Suddenly, we have one-dimensional structures that have restrictions in 2 dimensions. We will call this a quantum wire. Yet, no one home appreciates your cheese slicing abilities and hard work and demand little bites of cheese instead of strings. You give up and start cutting them in incredibly small cheese bites. You finally have quantum dots with electrons that are constricted to a particle. The cubic block may have had 6 faces being part of the surface area of the cheese, but with every slice sliced, 2 more faces appeared. You'll see now that atoms that precedingly were in the volume are now part of the surface, and now that you have trillions of more of these indistinguishable cheese bites, you'll see that up to more than 90% of the whole cheese now is in the surface. The quantum confinement effect is one of many ways that quantum mechanics tries to explain how matter and energy behave in an atomic level. When we analyze a particle that contains only a few atoms, we need to use quantum mechanics. When we analyze a macroscopic particle, for the most part we use classical mechanics, since there are so many atoms that the quantum effects can be negligible. Quantum dots are much closer to the size of atoms than to the size of a microscopic particle, so we need quantum mechanics to understand them. It is important to note that the particle's chemical composition doesn't change. To explain this, if we had a 1 meter diameter ball of cadmium selenide, a common quantum dot material, it is just a big semiconductor ball. Nevertheless, a 5 nanometer cadmium selenide ball is a quantum dot semiconductor. Size and shape of particles play the biggest role in this scenario. In the Advanced Nanoscience Lab of UTRGV, we study these materials for the broad set of potential applications for solar cells, LEDs, quantum computing, and medical imaging, among others. Our research focus consists on shelling these quantum dots into iron oxide magnets to create concise magneto-optical materials that can coax the electron hole band of the particle by applying an external magnetic field to the particles. This property can be measured by sending UV rays to our samples to have photonic emission from the quantum dots, making them glow at a constant wavelength. Using fluorescence spectroscopy, it is possible to compare the excitation spectrum versus the emission spectrum and compare these results when a magnetic field is applied versus when it is not. Using a physical property measurement system, an instrument capable of measuring the properties of a material as a function of the magnetic field, it is possible to plot the electron hole size change versus the magnetic field applied. Remember that for most people, quantum mechanics may seem complicated, but this is just because of the lack of exposure to it and misinformation. Now you know a bit about nanoscience in general and about quantum mechanics. Knowing about these phenomena and many more unleash the potential of scientific advancements to our century, and we can be a part of them. What invention can you imagine now that you have this information? Be a part of the conversation. Follow us in this channel for more interesting scientific videos. See you soon!